the less human interaction, the better. We are the source of the inconsistency. These devices that they're programmable and very consistent and can go down to very exact levels every single time. The more we can do of that, the less problems we have downstream.
Welcome to another episode of the Omni Pod, where we're enabling conversations between life science thought leaders to help you get the most out of your preclinical research.
Today, Caleb and Bill are talking about preventing cross-contamination in microbial assays.
I'm Bill Schick, Fractional CMO, and today I'm speaking with Caleb Proctor, Research and Applications Manager at Omni. Before we get into today's episode, Caleb, tell me a little bit about your background and how you got here today.
It's a long and windy road that doesn't make a lot of sense to many folks in kind of my scenario and in the research world. I started out with going down the path that a lot of people do when they go to college for biology is like, I want to be a doctor. I want to do all these different things. I want to be in medicine. And I got to the end of that 4-year degree and I was looking at the world and it's like, there's a lot of school and a lot of dedication left. And I really kind of just want to work. And so, growing up as a millennial, everyone says, get a STEM degree, STEM, I'm sure you may have told your own kids the same thing, right?
Yeah.
And in my mind, I graduated and I had this, this fancy degree of molecular, cellular, and microbial biology, right? And I'm like, where do I apply that at? And I just happened to luck into getting a job with a startup company in Huntsville, Alabama. It was called iCubate. It was inside of the Hudson Alpha Research Institute in the incubator that they have there. And so I dove in there, taking the work I had done from school and really applied it, working on creating a medical device that worked with pathogen detection. The first assay that we did was a gram-positive, the GPC assay, what they call it, gram-positive cocci assay. And it was detecting all these various superbugs that you've probably heard of before, MRSA, MRSI, and even like vancomycin-resistant things like that, like some very important organisms in the clinical world. And we got FDA approval from that and started developing the gram-negative test. And then I left there, kind of seeking to move to Georgia to be with my fiance at the time, and it brought me to Omni. And the cool thing about Omni is that they were looking for very much a generalist. And in my mind, I had been very focused on this one micro topic. But as we can get into later, like Omni, the samples that we kind of support here is everything from bones to bacteria, right? So you needed to be more than just one thing to work in this lab. And the universe is just whatever you want to make it here. You can run around and test different things all the time, help the customers, and have this just insatiable love for the unknown and a little bit of ADD, so I enjoy the day being a little different all the time. So it was a perfect fit for me. And but yeah, it's not the typical path for someone kind of going into a research environment. It very much was kind of chance for the most part, just getting into this world and sort of applying what I've learned throughout school and over the years into research here inside Omni with homogenizers.
What do you think you've been able to see or experience in this role that's a bit different than the one you thought you were destined for? What do you think?
I think a lot of it is getting to see how the sausage is made, right? On one end, whenever you're, especially in school, you sit there and they talk about the tests and they quickly kind of go through and it's like, and a positive result ends in this and you do these kind of treatments and blah, blah, blah. Here's the physiology of things, right? But getting to kind of dive into it here, you're really worried about the front end of it because that's really the most important step. And it's so often overlooked. And even today in a lot of research, you'll see this in the publications, right? And it's not for a lack of not caring, right? It's just sometimes it's kind of overlooked. For a really good example is you'll see people publish using our instruments and they won't publish the speeds nor the times nor the bead kits that they use with our devices to really showcase how they got to the result that they tried to get, right? And we know from our own research here, and I can post these application notes to really show this, is that especially with microorganisms, but even within tissues, that the proper bead matrix, the proper speeds to go with those bead matrices, and marrying that with the proper sample kind of really can dial up your results, right? So where I came from, we worked with, originally before Omni, we worked in blood culture model. There's a lot of organisms, right? And it was just for looking for positive detection. So it may not be a big deal to care about that step, but it may matter in the lowest end there. And that doesn't translate because they're not, that risk isn't being assessed, right, on the front end of in some of these papers. And it's kind of like the game of telephone where people begin to cite some of these different methods and they're changing slight, variations. Maybe it's we cultured for less time and they are applying these, less optimal settings, and that translates to worse data downstream. And so to kind of go back to your answer, like focusing so heavily on the front end of these workflows and the front end of this detection and really trying to dial out getting the most we can out of these devices with physical lysis was, it's just something that I took for granted, but two, never would have even considered before working here and working on these things.
I think that's a really interesting point. So if I'm used to some sort of manual homogenization process, what you're telling me is that the choice of my tools really actually makes a difference downstream. Can you talk a little bit more about that?
Yeah. So, we can. There's a lot we could talk about when it comes to manual homogenizers, right? People. The first thing in my mind whenever I hear a manual homogenizer is like a mortar and pestle, right? Mm-hmm. And then there's going to be people out there who use maybe a Downs or something like that. But we've worked with labs where manual homogenization is throwing a sample in like a vortexer empty and just shaking it in liquid and just trying to get a little bit of something to come off. And they would call that a homogenate. We've seen people who will, and we've seen this in the agricultural space and these are published methods. Like these aren't like somebody doing something crazy and off the wall. Like some of this stuff is peer reviewed and accepted, right? Of using pliers, like this is an AOHC. Like I would link it to you just for the comedic relief. Using pliers to crunch these seeds up to crack them open so you can extract out the nucleic acid. On one hand, like it's not really homogeneous, right? Because there's still a seed there. But on the other, there's a whole litany of other problems when it comes to cross-contamination, carryover, repeatability from Bill to Caleb, right? Like Bill maybe over here, just, little baby snips on his pliers. And then I'm, going full Hulk Hogan and cracking them open. And the second that you try to quantitate something off that, it becomes unquantifiable, right? That these differences that come through. And so where these devices come in is they remove so much of that. I often will say that we really only add value in 4 places to our customers. We will either speed up the time of processing, we will increase yields due to complete lysis, or we will provide consistency inside of these workflows. And the last piece would be we provide a way to innovate on top of existing workflows. And when we're talking about manual homogenization, like I fully believe that all 4 pieces of that value chain get added directly on top of a very manual thing. You're really only going to grind up 1 sample manually at a time, especially with a mortar and pestle. You're never going to fully lyse a sample unless you're just actually just going to town and really working on that single sample. So you'll get a complete lysis with one of our devices. The time is 1 versus 48. I mean, it scales so rapidly that you can see the time influence. And on the backside, you could turn this into something where the pliers instance, it's very inefficient, and maybe it's like this is how it's written, but all of a sudden now we can lyse it with an instrument. Like that just allows for innovation at a rapid scale, and economies of scale help on all samples when it comes to detection and analysis and everything down the chain.
I think those are all really good points. Something I'm kind of curious about is the plier story. Yeah. So I think there are a lot of equipment manufacturers out there that claim that they can process every sample. With that particular story, that must have been a tough sample to process. Otherwise, why would they be using pliers? Yeah. Can you talk about that a little bit more?
Absolutely. So in that specific one, that was a seed customer. They were looking for, and in agriculture, to kind of like back up and give a a good full view of that world, cost is incredibly important when it comes to processing these samples. So while there are likely more efficient ways compared to a pair of pliers, right? The cost of a pair of pliers is negligible when you consider the amount of uses, right? Like you can buy one pair of pliers from Harbor Freight and then come back with, you know, a $1 fix for these seed processing. The issue turned into this customer was trying to homogenize thousands and thousands of seeds at a time. And you could only, I mean, just imagine trying to convince anybody, much less yourself, that they need to sit down at a bench top all day and use these pliers to crack the seeds one by one and move them to a 96 well plate for analysis, right? Like it would take so much money for me to want to do that. You couldn't give me a podcast, you couldn't give me a playlist that would make me happy in this scenario, right? So for this particular customer, we were able to make it work inside of one of our well plates. The seeds were that not all seeds will work in a well plate. I mean, our well plates kind of are, you know, this is a sidebar, but some seeds will work inside of a well plate, others won't. The seed will be too big, the seed will be too tough. I mean, it takes a lot of effort to blow up some of these seeds, right? But we were able to make this one particular set of scenarios. It was if memory serves, it was a particular rice seed that we made work on this one. That we were able to get it inside well plates, and we were able to homogenize it and move it on down the line, and it created a high throughput extraction for this particular customer. It was so obvious, right? For them, it's just like, yes, there's this added value compared to something as reusable as a homogenizer, but on one end, it's saving my technicians, and it's also reducing costs in the form of reduced labor hours.
Right. That makes perfect sense. I think you had said something about cross-contamination, you know, across samples. Talk about that a little bit.
To kind of bring this back to the micro point of view here, typically, and really in any molecular assay, there is normally a zero tolerance for cross-contamination and carryover between samples. More so in a detection assay, right? It's not permitted to have an assay that's going to have so much cross-contamination between wells or between tubes that it's going to inhibit analysis downstream. We've seen some sealing methods where it's not a screw cap tube in a lot of these wells. A lot of customers want to work in something like a snap cap tube, and that's great for throughput. But sometimes when it comes to cross-contamination, it's not a great fit, right? Because there's not a great seal there. So on my end, I'm always looking for a perfect seal when it comes to the vessel that we bead in, and which one of those we want to marry with our homogenization process. On the flip side, we do have these rotor stator homogenizers, right? And sometimes there'll be workflows that'll have an assay that may be incredibly sensitive, where you don't necessarily want to have an open container, because our rotor stators is just this probe that goes down in an open tube, and like it or not, these open containers will have the ability to have particles, right, like microscopic particles, go between these tubes. So that is sometimes not conducive to assays that have this incredible limit of detection, right? I mean, if you look at some of these kind of bleeding edge techniques when it comes to, for example, like mass spec. Mass spec can detect incredibly low, we're talking about femto and lower grams of samples. And if you have an open tube where, there's an amount that's moving from tube to tube and it's going into there, like, that is untenable in the analysis part, because it will show up, right? Just downstream. It's just, you can't have that. So to bring that full circle on the micro side, with microorganisms, so often this is turning into a clinical assay, right? Like, there are people are researching some kind of workflow or some kind of sample preparation to feed that. The base amount of false positives they can have can't be greater than 5% of the entire workflow. They need a 95% positive detection rate. So with that being said, you start having this cross-contamination, that's a false positive. And or if you on the other side, you could lose your samples and you get a false negative, and those combine to become worse for these assays. So it's just kind of an untenable sample preparation.
With that in mind, how does a solution like the Ruptor Elite help me address something like that?
Yeah, so with the Elite, on one hand, you have tubes. So you have a lot of 2 ml tubes, you have 7 ml tubes, 30 ml tubes, 50 ml tubes, things like that. And in all of these tubes, we'll use especially in this case, the 2 ml tubes that have a good O-ring. I wish I have one here. I mean, it will probably won't show up on camera too well, but on the top part, we have an O-ring that closes down and cuts off that whole sample, so it's contained. I mean, whenever we blow up a tube from over processing it, it's because the vapor pressure inside this tube has built so much that it explodes, right? When you're working in tubes that don't have these O-rings, for instance, in a well plate or in a snap cap tube, you don't have that same level of containment in the tube. And when you don't have that, you run these risks of it coming out, spewing out with over processing, or it's just part of the processing. Or maybe when you're removing the cap, it's just sort of things are transferring in between the two. So the Elite, the beauty of the Elite is that it while it's not low throughput, I mean, it can be low throughput if you want it to, but we can put so many tubes on there that you'll have 48 at a time. And yes, you have to decap these individual tubes, but inside of each one of those tubes is a contained environment for each single point of analysis. And there's some power in that, right? Whenever you're really worried about cross-contamination and carryover, we can mitigate that. I mean, again, it's not as high throughput as a well plate. The well plates, going back to the sealed tube, the well plates are sealed with a mat. And it's good. In our well plate, we're happy with our well plate. There's other well plate seals out there, and I won't name names or anything, but I'll describe the issue. Some of them are sealed with a single layer of PCR film when they're homogenized, and that one little microscopic piece that's holding that edge down with an adhesive, when that gets compromised, the sample immediately goes to the next well next to it, and so on and so forth. So you can quickly contaminate an entire well plate with a sample, and if your assay's sensitive enough, you may not lose just one sample. You may lose 15, 16 samples in a line or in a big box around this one piece, and it's not that great. But we can mitigate this with using tubes, and then by using some small amount of automation on the back end with a variable pitch pipetter. There's various ones that you can use that are handheld. There's other larger, standalone automation units that have variable pitch pipetting devices. You can decap these tubes and put them on there, and then allow for this automation to move your semi-high throughput Elite homogenization step into a more high throughput analysis method. And it kind of, that little bit of automation bridges the gap to get you to where you need to go inside of a high throughput workflow. Because at that point, you're then marrying a minute or two homogenization into a very rapid analysis platform on an i6 well plate.
As opposed to doing it by hand.
As opposed to doing it by hand. Yeah, which takes forever.
So it makes sense that, in many of those cases, we would get cross-contamination where we would not want it. How do I build a workflow that I don't have to worry, whoever I put in place there can reproduce the work and follow the process and minimize or avoid cross-contamination? With
cross-contamination strictly in mind, from these samples to samples, the one of the very top end things that you want to do is you want to kind of set the stage from the get-go with that. So you're going to be bringing in samples that are individually packaged or individually secured, and then you're going to bring that into an environment where you can maintain that. So maybe you're working in a BSC. Maybe if these samples aren't necessarily pathogenic, maybe you're just working in like a PCR hood, but something to contain that outside environment from where the space you're working at. And that's pretty much SOP for most people working with very sensitive samples where they're concerned about this. Inside of our workflows, maybe it is something depending on how worried you are, is not opening all these tubes at one time, or leaving this well plate partially covered if you're working inside of a well plate. Our well plates, we're happy with our seal, but they don't have the perfect seal that these 2 ml tubes will have. So if you're working inside of a 2 ml tube with something that is very suspect, something that's very volatile that's going to be leaking out, which that would fail a lot of these tubes without O-rings or fail a well plate. You would want to reduce the head space that's in that tube by putting maybe more buffer in there so that you don't have any concerns with it spewing out vapor whenever you're cracking open these tubes. But working with one tube, one sample at a time, close it up, put it on the machine, put all 24, 48, however many samples you're working on, and use the homogenizer to your advantage, because you can actually program this thing in to be as tight as you want it to be. So let's pretend that Dr. Bill Schick is sitting here with his special snowflake samples, and he has spent the time to dial in his assay to the point where it is going up, and he sees signal increasing, and then once it flattens out, he decides that's where we're stopping. And so maybe he's laddered this out, and that's 26 seconds. I'm just pulling a number out, right? That's 26 seconds of homogenizing whatever sample you're homogenizing. The beauty of the machine is you can program that, right? If you've done the legwork on your end to say, I know exactly how these samples will work in this assay, then it's all going to be perfectly dialed in. So the leverage you have on that now is all of these samples are treated the same way. They can come off. Again, you can remove these samples, stack them in racks, maybe put them in some kind of automated device where there's very little human interaction, and the less human interaction, the better, right? When it comes to molecular techniques, because we are the source of the inconsistency. These devices that they're programmable and very consistent and can go down to very exact levels every single time. The more we can do of that, the less problems we have downstream. But at the end of the day, you really need to validate your whole method and think about these different points of contact and these different risks that each workflow is going to have, and then remove as much human element as you can.
Do you help your customers develop the application, the approach that they take, or the workflows to get to a solution faster?
Yeah, we absolutely have. I can't do everything, right? There's a very few of us, and there's a lot of different needs out there, and some of these things take a lot of time. But we have absolutely sat down with our customers in the past, and they'll give us a problem, and then we will try to get a really good path laid out for them. Most of the application notes that we've made come from those kind of setups where there's a customer that has X, Y, and Z QC, or they need X sample creating Y analyte, and that kind of drives a lot of our application development, because if there's one, there's probably more than one, and it'll help to go through that. But yeah, we absolutely have helped. We can't really validate for the customer because we don't have all the same equipment for them, right? And at the end of the day, they're people with their special reagents and their special equipment. All of these things are very expensive workflows. We can't have all the equipment, right? But let's say that they're doing a sequencing project where they say, hey, I'm doing a microbial community standard or something like that. They want to know that there's the metagenomic workflow is the best that it can possibly be. On our end, we've done a lot of work to show with standards that we can get a very good community standard result coming out of this extraction, and we give them that as a great starting point. In 99% of the cases, that one protocol for microlysis for DNA extractions is going to be the exact same protocol I give every time. It's only whenever you have very niche changes to that workflow that I would make some alterations to. For instance, let's say that you are working with an individual microbe and you only cared about that. We've got a lot of work, and I'll submit to you the poster and the application note for the community lysis. But let's say you're doing a single organism, like E. coli. There's all these other bacteria out there, but I'm just working with E. coli. Well, in our poster work, we showed the lysis over time with many different beads at one time, and you can see in the data that you have plenty of lysis early on, and maybe you don't need all of it lysed, and maybe you have very specific characteristics that you're after for, like, I want my fragment length to be as high as possible because I'm doing long read sequencing, or maybe I want my integrity scores to be higher, and then I would recommend, maybe a shorter protocol. But it's all dependent on very nuanced pieces of their workflow. So some things are more one size fits all, but there are times where we can tailor it down. But in my opinion, for me, I would want to try to tailor it as best as it could be anyway. And so I'm just looking for a good starting point on the front end, and then I will make the adjustments if I see so. So I think that fits pretty well. And that's not even including things like RNA. Like, I would change things differently for different analytes in total.
Right. It seems a very hands-on approach with customers.
Oh yeah, no, we love our customers, and we love to help where we can.
All right, Caleb, thank you so much. You were great today.
I appreciate it, Bill. Thank you.